Hello. Yes, I will be talking about hybrid quantum computing for AI. And I think that most of the conclusion we heard before applies to what I will be saying here. So first, a few words on myself. So I'm not a quantum scientist. I'm software engineering. I've been doing natural language processing, so as a PhD, and then I worked for 20 years for a company named Cistran. And I had the chance to experiment, to be in a domain where skepticism was dominant. In the 90s, or even in the 2010, people were not believing in machine translation. It was our business. Machine translation was translating one language to another language, and Cistran, my company, was working for already 40 years when I joined the company there. So there was this major skepticism around some technology that was nascent. And we worked on that. We worked on putting online translation. So the first online translation ever is Babelfish in 1999. When I joined Cistran, we put online the technology that was still not mature, that was still at its early stage. We put that on mobile. We put that everywhere. We wanted the technology to be visible. And I think it's part of the reason why it worked. And we were at the right moment, at the right time, when everything changed, when AI came. So we created some framework that was called OpenNMT, who had a huge impact on the community. So it was open source, and we were part of this transformation to AI. And I joined Quandela, so I flew away from AI at the point where AI was entering its golden age, because for me it was done. We had done the job, and I wanted to join some other adventure with the same potential. So I joined Quandela for that, and bringing the logic of product and bringing everything we've done for AI to quantum, and possibly merging the two of them. So I'm working for Quandela as the Chief Product Officer. So Quandela is a hardware company. We are building a photonic quantum computer. We are 120. We have 4 offices in Paris, in Munich, in Barcelona, in Seoul. And we have a lot of different talents in semiconductors, in electronics, in photonics, software development, algorithm, quantum information. So we are a lot, but at the same time, there is so many specialties at Quandela that's very hard to be at the top of everything. We have some production center. We are building our computer. We are a clean room where we are building our photonic source that I will be discussing a little bit. And we have a lot of research on algorithm too and applications. So some image on Quandela. So Quandela is doing this what you call single photon source. I will be describing a bit more what it is. So it's semiconductor. You see the scale of that. So it's very nice micrometric objects that are built in a clean room. We are working on photonic chip. We are integrating the single photon source into a standard semiconductor device, photonic development. We are building hardware. So this is the first quantum computer that we delivered. So a rack, a blue rack. So it was very nice, but it was not very efficient in terms of mechanics. So we changed the design a bit after. But we are building actual computers. And we are doing a lot of software development. And when I arrived, we launched a framework that's called Perceval, which is the equivalent of Qiskit for photonic quantum computing, how to program at lowest level a photonic quantum computer. So how does the photonic quantum computer works? So a small animation on that. So at the core of the hardware, you have 3 components. The first one is single photon source. We excite artificial atom with some laser that generates single photons. These single photons go into what you call a demultiplexer so that they arrive aligned spatially in a different modes, fibers. And then these 4 single photons go through some calculation stage, a photonic chip, where the interference between different photons produce a photonic quantum computer. One nice thing with photonic is that we are using photons, the photons that carry the quantum information. We are called like the flying qubits, and we can connect 2 quantum computers by a single optical fiber. It's naturally connected. So if you want to increase the capacity of photonic quantum computers, you just connect 2 computers with fibers, and it keeps its quantum properties. So at the very core, I won't go into detail on that, and I don't even understand, but Quandela is really has been built to produce this very nice object that I was mentioning. So it's artificial atoms, that is embedded into what you call micropillars, where and the atoms is artificial atom, but behave as a two-level atom. So we excite the atoms, and when the atom relax, then it generates a photon. All the photons generated are the same. So it is really the core of the technology. And to make it work, we need to collect the atom, because the atom will emit the photon everywhere. So we have this structure that is kind of a mirror, actually, what you call Bragg mirrors, and the atom is there, and then we want to guide the photon to go out, and then collect the photon into a fiber. So this is a technology that is at the core of Quandela. And then we build this very nice object. So this is the individual object. This is a sample with multiple of them. And then it looks like that at the highest level. And then it's integrated into this, what you call fiber pigtail device, where we just send a pulse of laser, and then we collect a single photon. Single photon, the quantum of light, which is the flying qubit. Then, when you have done that, it's easy, because we have a photon, we are room temperatures, and the single photon just need to interact, so interference. And here we are using on-the-shelf, almost on-the-shelf technology, photonic chips. So it is a silicon-based technology, and we just transfer to light, and the photons are going into the chips and are collected at the end with the interference pattern that they went through. And we have some control on the path of the different photons, so we can program this chip. But the chip itself is tiny, and then you have all the embeddings to the electrical contact on that. So this is the technology, and we put that as an end-to-end workflow. So we made our first computer online in 2022, and it has been online since then. So we have 3 generations since then. When I arrived at Quandela, the photonic quantum computer was looking like that, and we made something like that. So integrated everything. So it's you just plug that in, and it starts working. There is no condition, special condition to make that running. So when you think about, so this is for the technology. When you think about where we are going, so everybody is talking about we are the NISQ area where we have noisy, small physical system with short time decoherence. So for photon, it's not totally true, but it's not the point. And then we want all to go there. And maybe in the middle there is the utility. So the term utility was coined by IBM a few years ago, saying we are in the utility area where we are trying to find some useful application that will be outperforming brute force. So this is kind of the concept, and the grail is obviously this one. On my perspective, on our perspective, so I'm too old to hope that I will be playing with a fault-tolerant system that will be at scale, so I want to get the benefit of this area. But when we talk about utility, there is a lot of people and counter-arguments saying that it's simulable. So if it's simulable, then there is no utility. You can just run that on the GPU. The noise will kill any advantage that you can have. The quantum will be, in any case, too slow compared to a GPU. If you don't have fault tolerance, you don't have the phase shift, the phase transition that you will get with quantum, you can only get benefit from here with kind of paradigm that we hear from some company like PsiQuantum. PsiQuantum is one of the leaders of this statement. And some other people will say, OK, you are playing with light, basically, but you are not computing. So I want to kind of counter-argue on this point. And if we look at our own roadmap, so yesterday Professor Thomas Volz was presenting our system, a fault-tolerant system. So it is what you call spin-optical quantum computing. So the idea is quite simple on the paper. You take the same artificial atom that is somewhere here, and you start playing with the spin of the atom. So it becomes a matter qubit. So you have a quantum system, a matter qubit at the core of our system, and you play with the spin. So if you play with the spin, you can change the state, you can apply gates on different spins, and then you have a matter qubit system at the very beginning. And then this system is generating entangled photon qubits. So it's not just single photon, it's photons that arrive with entanglement. And then there is a protocol that has been called SPOC that shows how we can use that entangled strings of photons to make universal quantum computing under the framework that's called measurement-based quantum computing. So this is the end goal again, but what interests me is that to get there, there is multiple steps there. So we need to have these spin qubits that will generate this cluster state. We need to have some system that we call adaptive circuits, where we'll be able to dynamically reconfigure photonic chip. And it's not that easy because photons are fast, so we need to reconfigure a chip at the speed of light. So it's kind of a technological challenge. But we need, and there is a few other on the line, but we need all these components to get there. So whatever we do, we need to make this intermediate what I'm calling quantum primitives to get there. And the idea is that can we get any benefit from there? So we know that boson sampling is a primitive that runs on single photons on going to through an interferometer. There is a lot of debate on is boson sampling simulable or not? Can we get advantage there? Most of the quantum advantage has been claimed with boson sampling, but we know that there is a lot of algorithms that can compete with that. But is there algorithm that can compute with intermediate states? It's an open statement there. And if we look at the big picture, so of course we have our CPU. So a quantum computer doesn't exist; it's just a QPU part of a quantum classical computer. So we have CPU that can do almost everything very fast. There is GPU that can do a bit more slower, massive parallel computing. But it's good at most large matrix operations, tensor operations, some mathematical operations, but it's not good at doing anything, everything we could want. And the QPU, if you look at that side by side, there is only one core, so there is not a lot of people that can pretend to have multiple core quantum computer. It's very slow. It does only one simple task, what you call sampling. We get parallelism because there is entanglement superposition. So we have the intuition that there is something going on that we cannot compare with the other one. There is no or tiny memory in a quantum computer. And the line that really interests me is that it's good at doing very specific combinatorial tasks. So the idea is not to try to compare this guy to the other one, but to see is this line here can give me something, computing benefit. And if we look back at AI, and the AI, as we know today, it didn't come in one day. It came in 20 years of research. So we had this moment where suddenly AI was there, but it was there before. It was for more than 20 years. And it came with a lot of different components. So I won't go into details, but I've put them, I pinned them, most of them here. Different technology, algorithms that came out from research lab, from different university, and the collection of that, the sum of that, made what we have today. So plus the fact that you have big data, plus the fact that you have very big GPU, but in terms of software is as it is today because of the sum of these very simple, what I call primitives, in fact. We have these primitives that put together, for some reason, are giving the power of the transformer. The power of the transformer is what we have today at an even larger scale and with more technology that adds up on that. But the shift moment was the transformer that was just adding on different small primitives that came before. And if we want to compare that with quantum, so can I say something about quantum knowing that? What I can say is that it's not hardware that changed the world of AI. It's this primitive, this AI primitive. This AI primitive found a way. It was simulable because it was running on GPU. So the point about it doesn't have value because it runs GPU, I can cross it. It was running on GPU, and it brings a value, and it's a collection, the primitive by themselves that shape the MT. If we look at the quantum, so we have these primitives. The fact that they run on GPU is not a problem, because if they run on GPU but bring some value that the other one cannot do today or don't do naturally, then we have some value. And the value will not come from the speed and the compute power, but it will come by how the model will learn new information. So we had the chance. So we participated to the BMW Airbus Challenge in 2024 last year. And we had the chance to win the QML track. And there was two teams in Quandela. One was doing what you call QGAN, so it's a quantum GAN. So we say, OK, let us take the GAN algorithm and let us make quantum. And so the task was translating image from night to days and days to night. So the results were very, very bad. So it was doing something, but it was ridiculous. And we took another team, a team of data scientists, and they started from the very best state-of-the-art algorithm, and they just put some layers in this, so I won't go into too much detail there, but they just added a very tiny layers of quantumness that were bringing the state-of-the-art a bit higher. And we won because at the end we can show that we get 1% improvement in the accuracy, and we remove most of the hallucination of the model that was the state of the art. So it's not tremendous, it's not a night and day change. It is, actually it's night and day change because it's the task, but it's not a revolution, it's just an increment here. In increment in performance, we just added some value that the model that was super powerful running on GPU was not naturally able to learn. And the model was running on GPU. So it's not a question of GPU versus quantum, it was the way we presented the information to the GPU model was making the difference. Then we used that to introduce a framework that we call MerLin. So a few words about MerLin, this machine learning framework. So Perceval is the equivalent of Qiskit in the gate-based world. Perceval is for the photonic, and we wanted to have MerLin for the machine learning for photonics. So it was the idea. But the idea also was we wanted MerLin to be first on quantum-enhanced machine learning. It's not to make an algorithm that is quantum, it's to make an algorithm that is classical with a part of quantum. So the idea that we had before was we just want to make sure that it was just on the shoulder of the giants and not just on the side of the giants that we are trying to make this running. So we run on GPU first, simulator first. We integrate in PyTorch workflow, AI workflows. We make sure that it can run efficiently on GPUs and large-scale GPUs, so we made very high performance simulator for that. But at the end, of course, we want to go to QPU because the end is to run that on QPU. So we have the possibility to take small model and to fine-tune them on the photonic QPU. And also we put feature on the framework that doesn't exist yet on the QPU. We look a bit ahead. What will we get in 2, 3, 4 years? And the features are already there in the framework. So just to give some example of the kind of models that we can do. So there is some code here, but just for people familiar with how we build neural network in Python. So here we have a type of network that is very simple, but there is one layer that is a quantum layer. So we just need to make sure for that working in the complete flow, we just need to make sure that the 2 layers here are communicating together, 2 layers here are communicating together, so there is some kind of engineering to make that, but it's easy. This is another approach where we have some paths that is completely classical, and it is what you call quantum annotation. And we have some paths where we bring the same data into a quantum path, bringing some value that finally will be used by the classical layer. We have some approach where we can mix totally differently. For instance, in a GAN model, you can put a discriminator in the quantum with a quantum layer and the generator with classically or whatever. So we have the way to mix. We have also made another thing that we think that we believe are very powerful is the ability to combine matter qubit and photonic qubit. So, and the reason we are doing that is that it is where our technology are going. At the end of the day, when we have the Spock system, it will be matter qubit generating entangled photon that will go through a photonic circuit. So we made what we call the quantum bridge that is making connection between frameworks. For instance, in that case, it's PennyLane. We didn't rewrite that part. It's already working. But we just connect to make a neural network that integrates some PennyLane model, some MerLin model, and that run in classical PyTorch. And just to conclude, so with quantum, we believe that we have new unconventional quantum primitives. So it's not necessarily more powerful. It's not that they will be faster. It's not that they will solve the problem by themselves. It's primitives. We have these primitives that are coming, like transformer, attention model, word embedding came, that made finally the AI revolution. And we need to find workflows that can use them. Or maybe they don't exist. We are not sure. But if they exist, we need to find them. And for that, we need 2 things. First, we need to have frameworks open source framework, because it cannot be, if it's not open source, then there won't be any community, where we'll be able to run fast on GPU, because GPU is the only quantum resource that is available at scale today. We need to make experiment, benchmark, refine workflows, and that simultaneously. We need to combine quantum technology, not only photonics, because there is multiple quantum technology. We need to combine them in a single workflow. And we need to really go to what made AI a success, benchmark. Everything we need to do needs to be benchmark driven. So we need to have a way to measure an algorithm A with an algorithm B, even if B has a tiny part of quantum, even if B has no part of quantum, we need to make sure that we can compare them apple to apple and not apple to pear, as what we see in most of the QML papers that we are published today. We need to have open science. Open science means that when you publish an algorithm, a claim, you publish the code. And if you don't, then you don't have anything. In AI, it's the standard. We need to have the ecosystem. The ecosystem is the AI community. AI community is 100 times bigger than the quantum community. I would like to be able to have the AI community to look at the quantum primitive and to help us leverage them. And last, we need to think, and this is the most complicated part today, about how we will integrate that in heterogeneous HPC integration. At some point, we need to have a GPU talking to a QPU, talking to a CPU. How we can do that, knowing that all of them have the different speed of operations. Thank you very much.